Imagine a darkened room with a single light bulb. We could use a smartphone camera to measure the intensity, or brightness, of the light.
When the light bulb is far from the camera lens, the camera will capture a small amount of light. The intensity reading will be low. As we move the bulb closer, more light will reach the camera and the intensity will increase.
When the light bulb is closer to the camera, the light reaching the camera has spread out over a small area, as shown by this yellow circle. When the bulb is farther away, the light will have spread out over a larger area before reaching the camera.
Intensity is a measure of the power received per unit of area. If we assume that the light spreads out evenly in all directions, we can use the surface area of a sphere. 4 pi times r squared.
This is an example of a power relationship. The variable r appears in the equation as a power. As you may recall from math class, powers that appear in the denominator are considered to have a negative exponent. Thus, our hypothesis for this scenario is that the relationship between r and the intensity will be a power, with exponent -2.
In this experiment, the manipulated variable is r. This represents the radius of the sphere, or the separation between the light bulb and the camera lens. The responding variable is the light intensity measured by the camera.
Power is a controlled variable. We want the light bulb to produce a steady amount of light. To do this, we would use the same light bulb with a steady amount of electric current for all of our measurements.
We will record our data in a table. We can position the light, say 20 centimeters from the camera lens to start, and then increase the separation in steps of 10 centimeters.
At each separation, we can record the intensity of the light as recorded by the phone. We will continue to record data until our table is filled.
Once we have finished the experiment, we can draw a scatter plot of the data. The data turns out to be curved rather than linear.
There is a trick that we can use when dealing with curved data that follows a power relationship. Let's insert a new column into our data table. We'll use this column to transform our data, using our expected power relationship.
We had predicted that the exponent of the relationship should be -2. Take the first data point, I equals 0.2. Calculate 0.2 to the exponent -2. Record the result.
Now perform the same calculation for the rest of the data. 0.3 to the exponent -2. 0.4 to the exponent -2, and so on.
Now we will create a new scatter plot for the transformed data. We'll ignore the raw data in the first column, and instead graph the middle column along the x-axis. Be sure to label the axis as r to the -2 rather than just r.
If we transform the data using the correct exponent, the graph will now be linear. We can determine the equation that best models our data, just as we would for any linear graph.
First, add a best fit line. Next, identify 2 points on opposite ends of the line that can be used to calculate the slope and y-intercept.
In this case, our best fit line passes right through the origin, so we can use this as one of our 2 points. We can use a point at the top of the graph as our second point.
Use the points to calculate the slope of the best fit line. The rise is the difference between the two y coordinates. 35.0 minus 0. The run is the difference between the two x coordinates. 27.5 minus 0. The slope works out to be 1.27.
For units, the meters to the -2 appears in both the numerator and denominator, so it cancels. This leaves just watts for the unit of slope.
All straight lines have an equation of the form y equals kx plus b. Y represents the variable graphed on the vertical axis, the intensity of the light. K represents the slope of the best fit line, 1.27 watts.
X represents the variable graphed on the horizontal axis. This is r to the negative 2, not just r. B is the y-intercept, which is 0 for this data, since the best fit line passes through the origin.
We can take our theoretical equation and substitute it into a model equation. Both sides of the equation have r to the negative 2, so we can cancel these. Now we can algebraically determine the power of the light bulb.
Incandescent light bulbs are very inefficient, so the power calculated from our data is likely much less than the power printed on the light bulb. It may take 100 watts of electrical power to produce the calculated 16 watts of light. The difference represents thermal and infrared energy that the light bulb produces in addition to the actual light energy. Let's summarize the steps for analyzing data when the relations are power rather than just linear.
First, transform your data by calculating a power of each of your raw data points. Your hypothesis tells you what to use for the exponent.
In our example with the light bulb data, we calculated r to the negative 2, because our hypothesis predicted an equation with an exponent of negative 2.
Now graph the transformed data. If you transformed the data correctly, the graph should be a straight line.
Now you can add a best fit line and calculate its slope and y-intercept, just as you would for any linear graph.
When you write the model equation, y equals kx plus b, remember that x refers to the transformed data, which includes the exponent, not the raw data.